Okay, welcome back. It's the third part of the radiation and moving heat around part of the lecture here. And now that we know about the different things that can happen when radiation is moving through materials, be that the air or clouds or greenhouse gases or ozone or whatever, or hitting surfaces like the surface of the Earth or the roof of a building or your solar array or whatever, we can start talking about Earth's radiation budget. And when we're talking about radiation budget here, we're just talking about like keeping track of where radiation is coming from and where it's going. And this is kind of a standard trick in the atmospheric sciences. We like to think about things in terms of budget. Budgets of moisture. Where is moisture coming from? Where is moisture going? Budgets of pollutants. Where are the sources of those pollutants and what processes remove those pollutants? And in the same way, we're going to have kind of a budget for heat or radiation to the Earth's atmosphere. And we're going to be building a chart over here on the left side of the screen here. During the day, we're going to have a source of shortwave radiation, namely the sun, up high in the sky. And the solar radiation is going to be shortwave radiation. We're going to use the symbol SW to mean shortwave radiation. So shortwave radiation, as I've said before, is in general transmitted through clear air. Yeah, there are some processes that cause the amount of solar radiation that is moving through the Earth's, downward through the Earth's atmosphere to be attenuated or reduced. You can lose some of your shortwave radiation by absorption by ozone. Some of it is reflected by clouds along the way. Clouds are really good at reflecting solar radiation back up into space. But a certain amount of radiation from the sun, a certain amount of shortwave radiation, is going to make it to the ground. And the notation that most of the textbooks use for that solar radiation that makes it to the ground is SW down, for shortwave down. So the shortwave down is the amount that we measure down at the surface that has reached the ground. Now, when this radiation reaches the ground, well, first off, shortwave down obviously will only be not zero during the day. At night, there's no shortwave reaching the ground. I mean, you could talk about moonlight or you could talk about starlight, but good luck running your solar panels on moonlight and starlight, right? Good luck warming up the Earth's atmosphere using moonlight or starlight or whatever. A certain amount of this shortwave radiation then will be reaching the ground. We call that shortwave down. That's the part that actually got to the ground. But the ground has an albedo. A certain amount of that radiation will get reflected back up into the air above us and head back up towards the sky. That fraction that starts heading back up is called, that part of it is called shortwave up, SW up. So a certain number of watts per square meter of this radiation, of this power, will reach the ground. Watts are a unit of power. Watts per square meter is the flux of that power at the surface. A certain number of watts per square meter of power, of solar radiation, will reach the ground. A certain amount of that will be reflected up, that shortwave up. The net shortwave radiation is the difference between the two. Shortwave down minus shortwave up will be the net shortwave radiation. That is the amount of radiation that hit the surface of the Earth and was absorbed. How do I know it was absorbed and not, say, transmitted? No solar radiation is transmitted through the surface of the Earth. If you go even a centimeter down into the ground, it's dark. There's no solar radiation being transmitted through the ground, much less all the way through, and comes out the other side of the Earth, right? So any radiation that isn't reflected off the surface of the Earth is clearly being absorbed. And the net amount of solar radiation that we are absorbing is SW net. SW net will be zero at night, where we're not getting any solar radiation, and it will be a positive number during the day as we are gaining solar radiation. Now, we're going to be talking more about the factors that determine that shortwave down in a little bit, in particular like the sun angle, how high in the sky the sun is, and the length of daylight, how long the sun is up, later in this lecture. But both of those things turn out to be functions of both the latitude of the location you're talking about and the day of the year it is, and we'll get to that in just a little bit. But this business of the shortwave radiation is only kind of half the story. The other side of the coin is what happens at night. Well, okay, let's be more fair. It happens day or night, and that is the business of long-wave radiation. At night, there's no shortwave radiation going on, but there is long-wave radiation. It actually happens during the day too, but we'll draw it on the half of the diagram here that's at night. Now at night, the Earth's surface is emitting long-wave radiation. Day or night, actually, the Earth's surface is emitting long-wave radiation. The Earth is made of matter, therefore the Earth's surface emits radiation. The amount that the type of radiation, according to Wien's law, that it emits is going to be long-wave radiation, like infrared and microwave radiation. If we had a sensor here, a radiometer, that was measuring the flux of this long-wave radiation, we could measure the flux of radiation near the surface of the Earth, and we would call that LW up, for long wave up. Long-wave radiation is emitted by the surface of the Earth. That's a cooling process. That emitting that radiation is reducing the surface of the temperature of the Earth. That long-wave radiation is headed up towards space, and some of it will actually escape right up all into space. Although in practice, the gases in the Earth's atmosphere, especially the greenhouse gases and clouds, are really good at absorbing long-wave radiation. Not very much of it actually gets all the way up out of the atmosphere, at least not initially. On the other hand, the greenhouse gases in the Earth's atmosphere and clouds in the Earth's atmosphere and so on are also really good at emitting long-wave radiation. So at any given time, you could take your radiometer that measured the long-wave radiation coming up and turn it around and point it up at the sky, and you would see that there is long-wave radiation coming down from the sky, LW down. And long-wave radiation from this downwelling long-wave radiation came from like the greenhouse gases and clouds and so on. Which means just like we had a shortwave net that was the difference between the amount of shortwave down and the shortwave up, we also have a long wave down and a long wave up. We're emitting some long wave radiation at the surface of the Earth, but we're also getting some long wave radiation from the sky. The difference between those two is the net long wave. Are we emitting more long wave radiation than we are absorbing? Then maybe our temperature will go down. If we are absorbing more radiation than we are emitting, maybe our temperature will go up. But it's not just the short wave and it's not just the long wave, it's actually both of those factors. Where the net radiation at the surface is the difference, it depends on how you define the signs here. You would include the shortwave net and the long wave net. I wrote it here as minus. It might be, if you thought through the signs, maybe you'd want to put plus there. Whatever. We'll do this in more detail when we start talking about like predicting the heating and cooling needs of an area and so on. But you can see how there would be these two factors. I mean, it just depends on the signs as to whether you're going to use where you're going to define it as positive or negative. You would need to know the net amount of shortwave radiation the object is gaining and the net amount of long-wave radiation. If you're losing more radiation by long wave than you're gaining by shortwave, this is going to be a net cooling process. You're losing more radiation than you're gaining and your temperature is going down. That's what's going to typically happen at night. Typically at night, you have no shortwave radiation and you are losing heat by long-wave radiation up, so this net radiation is down, is negative, you are cooling. During the day, generally speaking, the shortwave net is greater than the long wave. You're gaining more heat than you are losing, and the temperature goes up. Notice the role here, by the way, of these greenhouse gases like carbon dioxide, methane, water vapor, etc. They are gases that are in the atmosphere that are really good at absorbing long-wave radiation. And as a consequence, we call these greenhouse gases and their effect, we call these the greenhouse gases, even though it doesn't have very much to do with how a real greenhouse works. And they're going to be creating what's called the greenhouse effect. The greenhouse effect we'll learn more about later in the fourth part of this lecture here. But I want you to notice the effect of the greenhouse gases was to take some of that long-wave radiation that the surface was losing, absorb it, and send it back down towards the surface of the Earth in terms of long-wave down. That has a net effect of keeping the planet warm. That's a natural part of the Earth's atmosphere system. If we didn't have that going on, that we'd live in a very different planet. But we'll talk more about that in the fourth unit of the class. I also want you to notice, by the way, the complex business of the role of clouds in the Earth's atmosphere in the radiation budget. I mean, notice that during the day, clouds were reducing the amount of shortwave radiation that made it to the surface of the Earth because they were reflecting this radiation. But both day and night, clouds are also part of the greenhouse effect. They absorb long-wave radiation and emit long-wave radiation back down towards the surface of the Earth. The role of clouds in the temperature budget or the heat budget, the radiation budget of the Earth is actually an incredibly complicated phenomenon. It's one of the sources of uncertainty in our understanding of global warming and the greenhouse effect. Many of those questions have now been answered as to how that all works, but it is a complicated role, and we'll see more later in the semester about ways in which clouds complicate things like our understanding of how much electrical production we'll have on a solar array and so on. Now, before we move on to the fourth part of this lecture, though, I do want to ask you a third question here. During the day at a given location, which is going to be greater, shortwave up or shortwave down? Now, I'm not trying to play any games here with signs, just kind of think in terms of absolute values here, if that's helpful to you or whatever. Again, especially the atmospheric science majors and minors who are in this class might get themselves a little bogged down about thinking, oh, but is shortwave up positive or negative? I mean, it kind of depends on what classes they've had and stuff like that. Just think in terms of absolute values here. In terms of absolute values, which is greater, shortwave up or shortwave down during the day? All right, so here's a given location. If I just measured shortwave up and shortwave down, which is bigger, shortwave up or shortwave down? Look through those choices, and then below this video, click on the one that you decide is the right answer to move on and get a little feedback before you see the fourth part of this lecture.